Thank you. So, I'm here today to talk to you about superintelligence, where AI might go, but I want to bring people back and ground us down in the science that the last speaker spoke about. I think it's critically important that we do realize enthusiasm alone won't bring about these technologies. It'll probably be through long, dedicated efforts of scientists and engineers who struggled through academic careers to understand the deep science that lies behind these issues. But first, I want to show you my favorite picture of a dinosaur. This is important because this is actually from a webcomic, and it's a serious proposal for how to increase the awareness and excitement of students in the sciences. Its proposal is, put this picture in the front of every textbook for science, and put the caption that says, "Screw real-life applications." You want kids to learn science? Put this here and say, you can ignore this book, go ahead, coast through this class. But one thing in life is certain. Someday, someone will clone a dinosaur. And that someone will be an expert in a million things you think are boring right now. And if you don't study and work and think, one day, you'll watch that person saddle up, put on a cowboy hat, and ride a T-Rex from a monitor in your cubicle while your boss yells at you to stop wasting company time. I think this is instructive, and so a lot of times at the Singularity Institute, I often interview people that want to work for us as researchers to help develop the next level of super AIs, things that might be able to take on some of the science and other roles. Even if you're an AI skeptic and concerned that maybe full AI is impossible, probably something like an AI scientist is possible, something that can help augment our abilities to do science. And so I think it is pretty realistic to say that, we can go from here, a big set of mainframes with tons of AI scientists on them, to here, with our cloned dinosaurs, so that we can go on a little ride. But the path through this is a really interesting intellectual journey. And so I'm giving this to try and let you know that at mainstream universities all over the countries, there are shared programs where you can teach yourselves the basics of what it would take to design a mind. Cognitive science, this is where you'd start. We're the only known example of general intelligence. So, learn the few things we know about it. Right now, we have very parallel architecture, highly redundant, many specialized little units. But the other side of that is our brains also fail us. So a course in heuristics and biases could teach you quite a lot. For example, evolution designed our brains so that if something takes over 100 sequential steps to process, your brain just gives up and gives you the first answer it came up with. But it doesn't tell you this. It just gives you the answer and makes you entirely overconfident in it. This is probably something we want to shy away from as we design better and better minds. Functional programming is something I think totally underemphasized in science, computer science, and math disciplines. It used to be popular, and people went away from it towards imperative programming, things like C++, Java, and away from Scheme and Haskell. But the benefits of functional programming are that you can actually do machine proofs and check to see if your code matches your spec. This will be important later because you can do safety checks on it. Discrete math. Everywhere in the sciences, people are pushing continuous math because it's very interesting. A lot of relativity, electromagnetism, some physics branches made incredible breakthroughs with continuous math. Unfortunately, all of computation uses discrete math. And most people don't study this. People study higher and higher forms of calculus, which aren't very useful for designing advanced AIs. So yeah, don't learn higher and higher forms of calculus. You should instead learn things like linear algebra. This is totally foundational to probability and comes up in everything else because probability is a main input into how artificial intelligence will work. Almost all kinds of artificial intelligence that we could design. Set theory, I want to start a series of analogies here. If you think of mathematics as reading, then set theory is like learning how to build letters into words. And it's exactly the same. Normally in set theory, you build axioms up into theorems. Same thing with mathematical logic, which is the next step, where you build words up into full sentences. Some of them make more sense than others. Some of them are very useful. It's useful to know mathematical logic. For instance, the logic on this purports to prove that God exists. There's a flaw in this proof, but you would need to know mathematical logic to see it. Algorithms. This is like building up sentences into full paragraphs. Algorithms are the recipe of thoughts, and any advanced artificial intelligence that's built on computers is going to use these. But one thing that people usually don't do, so lots of computer scientists learn about algorithms. Most of them don't learn about numerical analysis though, because in the math department. But numerical analysis shows you how to make sure that tiny errors in your input streams don't cause big errors in your output streams. Basically, you can nobly design algorithms that are more resilient to errors. And this would be very, very good if you want your AI to perform well. Computability is sort of the top layer of this analogy. This is where you're no longer building up words and sentences and paragraphs of computerized thought, but you're looking at all the possible things that can be written. Well, almost all the things, because there's actually one more capstone of quantum computing, where you can go and learn things that aren't yet physically able to be computed because we don't have large copies of quantum computers, and likely won't have them before we develop advanced AI, but it's still useful to know the bounds of what's theoretically possible to be computed efficiently. Parallel computing, on the other hand, is definitely going to be useful. No matter how good we are at designing algorithms, we're probably going to have at least a few that are inefficient and difficult to make efficient initially. Those are the things that we're going to throw a huge amount of computers at. And the good thing about parallel architectures is, even though there's some difficult, tricky things, most of the theory is solved. It's just an implementation thing. So you're not going to need to develop a deeper understanding of parallel computers than the field already knows. Program verification is a pretty mature field too. Right now you can only verify things that are a few thousand lines of code though. Hopefully this becomes more efficient, but if way back in the beginning you learned functional programming and went down that path, you might have a chance of being able to code check your code and see if the specs match the code. Certainly this doesn't guarantee safety. Your specs have to be right and your specs have to be safe. And then you have to get it right. But introducing random errors that you don't even know about and making your spec deviate from your code definitely won't improve situations. We know empirically that every time you take a functional verifier and you run a huge code base through it, they find large, embarrassing errors that programmers made. So basically you have the choice between making large, buggy code or large, possibly working code if you run it through program verifier. And then we have to exit out of just computer science, head back to math, and learn about probability theory. Life is uncertain, and AIs are going to have to deal with that uncertainty. In fact, they're going to have to combine their knowledge of multiple uncertain situations using Bayesian modeling. And then, as a scientist, AI scientists desperately need to understand probability theory deeply, because this is what statistical machine learning is based on. And we know, since we don't have enough understanding to build AI scientists, that we need more understanding in this area. There's a couple more courses I would recommend. Statistical machine learning. Artificial intelligence, They teach a course called this at university, and even the leaders in the field will tell you the princess isn't in this castle. You've got to go back and study more deep foundational math. Probably the key lies in cracking the self-reference problem, which will require things like studying Gödel's theorems, metamathematics, model theory, and even category theory, so that you can import ideas from one section of math into another. There's other recommended reading that I would recommend AI scientists look into. And if this sounds like an outline of your course syllabus from when you were in school, please get in touch with me. I want to hire people that want to work on machine superintelligence. Thank you.